Okay, so in the last session, we studied propositional logic. So now we'll move on to predicate logic, which is more complicated than the propositional logic, but takes care of a lot of things, and it becomes easy to represent anything using predicate logic. So, like we saw in the previous session, propositional logic is actually very difficult to use because it cannot represent a lot of things. So, it's a very simple logic. And some complex environments, it will be very difficult to represent using propositional logic, especially if it has many of the same propositions for say different time points or different indices, etc. So if you have to keep repeating the same thing, then the number of propositions goes up a lot. But at the same time, since it's the simplest type of logic, we first understand the concepts of logic using propositional logic, and now we move on to predicate logic. So the predicate logic consists of objects and properties of objects and relationship between objects and functions. So it makes use of all these and makes it easier to represent things in the real world. So just like you have the natural language which can represent nouns, verbs and relationships between verbs, nouns, etc. We need to have the first order logic which can represent whatever you can represent in a natural language. For example, in English, whatever we can represent, we should be able to represent in first order logic. So what is it that we can represent? Like we said, objects, relations, functions, properties. So objects are like people, houses, numbers, names of people if you take persons, colors, games, wars, centuries, lot of things are objects. And then the relationship between objects. The unary relationship is the properties of the object. For example, we can say a red ball or a round ball, bogus, prime number, etc. So these are all unary relations. So the relationships are properties of one particular object. And then you have n-ary relationships, which will consist of more than one object. Brother of, bigger than, inside, part of, has color, occurred after, owns, comes between, etc. And functions like father of, best friend of, third inning of, one more than, beginning of, etc. So the difference between functions and properties would be that functions will be a function between variables. So for example, you can say that if x is a person and y is a person, then if they are siblings, then it will say siblings xy, etc. So father of means it will say, it will use the proper relationship, but it will use variables. So when you use variables, you call it a function. So let us look at some example sentences. So you could take any sentence in English and you can break it down in this way. So if we take 1 plus 1 equals 2 equals 3, it says here. So 1 plus 2 equals 3, right? So the objects here are 1, 2 and 3, and the relationship is equals and the function is plus. So that's how you can break down the sentences. The color of the sky is blue. So the object we are talking about here is the sky and the property is blue and the relationship is color. Squares neighboring the wumpus are smelly. So what are the objects here? So wumpus and squares, and the property is smelly and the relationship is neighboring. Evil King John ruled England in 12,000 AD, say. So the objects here are John, England, 12,000 AD, etc. And the relationship is ruled. The property is evil king, etc. So in this way, any sentence you have, you can break it down into these different characteristics of the sentence. So the first order logic is mostly consists of objects and the relationship between objects, or the relationship between an object and itself, etc. Another thing that first order logic can do is it can express facts about some or all objects in the world. For example, we can say something like all crows are black and things of that sort. So, which means that you are expressing a fact about all the objects of one type in the world, or you can express the facts about one particular person, so that there exists somebody who's got this property or some such thing, right? So we'll see more of that later. And this along with the implications and connectives. So the connectives implication also is a connective basically, right? So these are what is used to represent anything in first order logical, first order logic. And what are the things which cannot be done using first order logic? One is time and events. So you don't know how to represent events, how to represent time, or categories. For example, you can have a category of edible foods, or categories of tomatoes or whatever, right? And those will have certain properties, etc. So we'll see how to represent these things later on in time, but as far as first order logic is concerned, you can't represent these things, categories, times, events. Okay, say Shankar flew from New York to Delhi on such and such a date from that time to that time. That is an event, right? So how do you represent events? And then when we talk about first order logic, what do we mean by first order logic? So there are some things which cannot be represented in first order logic. So in first order logic, we can represent relationships and functions, okay, and we can represent, you can make assertions, but in the case of higher order logics, you can use relations and functions and view them like you use objects in the lower order logics. So this is something we have seen, the ontological commitment and the epistemological commitment. So when you talk about ontological commitment, what is it that the particular logic is able to do basically in the knowledge base, right? So we can see in propositional logic, you have only facts, and in the first order logic we have facts, objects, relation, which makes it little more versatile. And in temporal logic you are adding time to that. We'll see later how we can take care of time. And in probability theory, of course, you are using facts, whatever, but this epistemological commitment, or what does the agent believe, okay, about these facts? True, false, or unknown in the case of propositional logic, same here in the case of temporal logic and first order logic. But in the case of probability theory, there is a degree of belief from 0 to 1. And in the case of fuzzy logic, the facts also have a degree of truth. So we'll see these type of logics later. First we'll see the first order logic basically. So So you have symbols which you use, okay, which stand for objects, relationship and functions. What are the types of symbols that you can? The constant symbols. So the constant symbols are, we started with a capital letter. So you can say A or B, P, Gita, whatever, right? So those are objects, particular object. And you have predicate symbols which stand for relationships like round, brother, etc. Then we have function symbols, cousin, father of, etc. And terms. So, a logical expression that refers to an object. A complex term is formed by a function symbol, okay, followed by parenthesized list of arguments. So atomic sentences state some particular fact, okay. It's got a predicate symbol which is followed by a parenthesized list of the terms. For example, brother, Rama, Lakshman. Atomic sentences can have arguments that are complex terms. So inside the atomic sentence you can have a complex term. So married, father of, so you are using a function here, father of Rama, mother of Lakshman. Okay, so this is an atomic sentence, but the arguments are complex. Then you can have complex sentences by using the connectives. So just like in the propositional logic, here also you can use connectives. So you can say brother Rama Lakshmana and brother Lakshmana Rama, older Rama 30 and younger Rama 30. Older Rama 30 means Rama is older than 30 years old or he is younger than 30 years old. So that's what that means. Older Rama 30 implies not younger Rama 30 and not brother Rama Dilip. Okay, so these are the ones with the connectives, different sentences which you can make with connectives. And the quantifiers, there are two basic quantifiers. One is made for all objects of a particular type. So you say, for example, use the symbol here, and these quantifiers are basically followed by a variable. So when you say all crows are black, say for all x, so x is a variable which you are using, crow x implies black x, which means for all x, if it is a crow, then its color is black. So for variable we use small letter, and for other things we use the capital letters. So this is called the universal quantifier because it is true for all objects x in the universe, right? And suppose you have a term which doesn't have any variable. So we saw what is a variable. Variable is always introduced by a quantifier. So either you'll be using the universal quantifier or you'll be using the existential quantifier, which we will talk of next. And you introduce a variable with that. Now if you have a sentence or a clause which doesn't have any variable, it's known as a ground truth, because you don't have to instantiate that variable and say, okay, X stands for John or X stands for Gita or whatever, right? So the existential quantifier is like this, okay. It makes a statement about every object. We may make a statement about some objects in the world, not all objects. So Spot has a sister who is a cat. So you say that exists X, sister X Spot and cat X. So this is the second quantifier that we talk about. Now these quantifiers can be used more than once in one sentence, right? So you can have nested quantifiers. So you can have nested quantifiers with different variables, right? So if X is parent of Y, Y is child of X. So for all XY, parent XY implies child by X. Okay, so here we have nested, we have two universal quantifiers together. So you could also say for all x, all y, but this is a simpler way of putting it. A person's brother is his sibling. So again we take x and y, brother x, y. So y is brother of x means that sibling yx. So y is the sibling of x. Everybody loves somebody. So for all x, that is everyone, there exists some y loves xy, right? So these are nested quantifiers which you are using. And a well-formed formula is a proper sentence where every variable is introduced properly. So you will be introducing every variable by using one of the quantifiers. And when you are using nested variables, they should be, of course, using different names. So if you can't use both x and x for these, right? If you will have to use different variables for each of them, basically. Okay, so what is the connection between this for all and that exists? Okay, the universal and the existential quantifier. Okay, so they are actually very much connected with each other. Okay, so the one is the negation of the other. So we can actually see this very well. Okay, see, we suppose we have a statement which says everyone dislikes carrot. We can also say there does not exist anyone who likes carrot, right? So you can see that there is a connection between the two. So when you say for all x, not likes x carrot, you can also put the same sentence as there does not exist x likes x carrot. So basically if we take the first sentence and we negate it and we, instead of the universal quantifier, we change it to the existential quantifier, you are going to get the second sentence. So we can say that there is a connection between the two. Everyone likes ice cream. Okay, so we can say all x likes x ice cream. But we can also say this in the way that there is no one who does not like ice cream. So again, if we take a negation of this, you are going to get there does not exist x not likes x ice cream. So we can see that they are actually a negation of each other. And this is true because when you use a universal quantifier, it is a sort of conjunction, whereas the existential quantifier is a disjunction, and they obey also De Morgan's rule because of that. Okay, so what was De Morgan's rule? De Morgan's rule said that, so suppose I take A and B and take the negation of this would be equivalent to not A or not B. Similarly, if we take not of A or B, this will be equivalent to not A and not B. So this rule is also followed by the quantifiers. So suppose I say for all x not p, you can say there does not exist x p. Okay, so you are just negating this and putting exists instead of the universal symbol. So not of all x p will be the same as there exists x not p. So we can say that these also follow De Morgan's rule. So this is equivalent to saying not of p or q is not p and not q, etc. Right? Not of p and q is not p or not q, etc. So we can see that we don't really need both these quantifiers. That is, with just one of the quantifiers, for example, if we have the universal quantifier, we can also represent the existential quantifier part. But for the sake of readability, making it easier to understand a better way of expressing things, it's good to have both quantifiers, and so both quantifiers are basically being used here. And then you have the equality symbol. So father of Kumar is equal to Mohan, right? So you are saying that father of Kumar is the same as Mohan, both are the same, right? And the equality symbol can be used to state facts about a given function, and it can also be used with the negation to insist that two terms are not equal to each other. So for example, if we say that Dilip has at least two brothers, we can write there exists xy, brother x Dilip and brother y Dilip, right? But if I write this, then suppose x and y are the same, you're talking about the same person as x and y since they are variables, right? Then it does not really give the intended meaning that he has at least two brothers. So you got to add this thing which says that x not equal to y. So this term x not equal to y or not x equal to y. Okay, so that needs to be added over there. So that's the equality symbol which we can use here. Okay. And then location, how do you keep track of? You can use xy coordinate, angle. You can say things like adjacent, one is on top of the other, one is below the other. So you can use some quantitative way of keeping track of the location. And you can have preference among actions, great, good, medium, etc. So this gives the Backus-Naur form for predicate logic, and we can see that it's a lot more complicated than what we saw for the propositional logic. So again we start in the same way. A sentence can be either an atomic sentence or a complex sentence, and the atomic sentence consists of either a predicate, so you could just have a predicate A or B or P, etc., or a predicate with a term, okay, or you could say term equal to term, you can have something like that. So all these are atomic sentences, and you could also have complex sentences which consists of sentences with parentheses and all the connectives, right, and all the quantifiers that you can use. So you can have a quantifier, variable and sentence, etc. So all these are complex sentences. And what is a term? A term could be either a constant, it can be a variable, or it can be a function with terms inside, right? Then what is a quantifier? There are two quantifiers. What are the constants that you are using? So we have said here somewhere that we are using a constant, right? So the constant that we use are all these constants, and the variables you use are x, y, z, etc., and the predicates, okay, and the functions. So these are all the things which go into the predicate logic basically, and of course the same operator precedence also comes here. So again we have not followed by the and or implication, double implication, equal to, this is right. So this is the operator precedence. So this whole thing gives you the syntax of the first order logic by using the Backus-Naur form basically. So when you talk about a well-formed formula or something which follows the rules which are laid out in this, so if it follows these rules, then we say that it's a well-formed formula in predicate logic basically. Now when you come to higher order logics, it's got more expressive power than the lower order logics. So what we have is now first order logic. So in first order logic you have quantification over objects, okay, but in higher order logics you can have quantification over relations and functions also. So let us take some example here and see how it works. Two objects are equal if and only if all properties applied to them are equivalent. So two objects x and y, okay, so suppose we take for all xy, x equal to y, this will imply that or use a double implication, because if and only if is being used. There are, if you consider property of x is equal to the property of y. So if a property is applied to x, the same property can be applied to y and they will be equivalent to each other. And the next sentence is two functions are equal if they have the same value for all arguments. So we have two functions f and g. So we are using quantifier on the functions and we say f is equal to g if and only if for all x. Okay, so for all arguments x, f of x is equal to g of x. So this is what is different in the higher order logics. So this can be added into the higher order logics. Okay, so how do we use the first order logic? So we can see that in the case of first order logic, this you can make sentences about anything in the world. You know, it makes it very easy to use the first order logic. And when you have a knowledge base, you can have something called tell and ask, which I had talked about earlier actually. So when you say tell, it means you are telling some fact to the knowledge base. So basically the syntax of that will be like this. So you say tell and the knowledge base. So the particular knowledge base you are talking about, okay, to that knowledge base you tell this particular fact. So these facts or rules that you are going to enter here will be in predicate logic basically. So you are telling the knowledge base that King John, that John is a king, and you are also telling the knowledge base that Richard is a person. And you are giving the knowledge base this rule which says that for all x, king x implies person x. So if somebody is a king, he is also a person, right? So this is the way you keep adding information into the knowledge base, and when you want to ask a question, you can use ask. So ask knowledge base King John. So if you give something like this, it means it checks whether this is true or not. If this is true, then it will return the answer as true. Otherwise, it will give it as false. Okay. And you may want to know the value of x, right? Suppose I say ask knowledge base person x. Okay. So one type of knowledge base, you use something called ask where instead of using ask. And when you say ask the knowledge base person x, you are trying to ask, if you take person x, who can be substituted for x there. So there are two substitutions possible here, x can be John or x can be Richard. So we write it in this way. Okay, so for x you are substituting John, and also you can, for x you can substitute Richard. Okay. So this is called a substitution or binding. So you are finding a binding for the variable. So we can take this particular thing here where you are telling the knowledge base this particular information for all MC, mother of child is equal to M implies that female M. So M is a female and is a parent of C. And you are saying, another term you are putting is that female maxi and parent maxi spot and parent spot boots, right? So, and you ask the knowledge base whether grandparent maxi boots. Okay, so it may be having a rule in it which says that if one is a parent of another and that one is a parent of another, then you say grandparent. So it will give the result as S. And if you ask the knowledge base, there exists X child X spot, and it will find the binding for X. So it puts X as boots. So what we will do after this is we'll take a number of different domains and we'll see how using predicate logic we can get statements in that particular domain. So, we will do this in the next session.